Hey everybody, in this video I'm going to talk about geometric modeling, and the key idea here is that we can use, I'm just going to do a semicolon, or that's just a regular colon, use shapes and other solids to represent physical or real world objects. And then with these shapes or solids, we can approximate their measures. So I'm going to say use shapes, solids to represent real world objects and approximate their measures. Now, what you can determine about an object depends on whether it is two-dimensional or three-dimensional. So two-dimensional shapes are what we call 2D shapes, have length and width, like a rectangle or a triangle has a base and a height. Two-dimensional shapes, a circle is considered two-dimensional versus a three-dimensional solid shape or a three-dimensional figure. Three-dimensional or 3D figure, which has length, width, and height. So a square, that's our first example. A square can become two-dimensional, when I make it a cube. Here's my square. Now I'm adding some depth to it, really. We oftentimes like to think about it as. But I now have a length, a width, and a height. You can have cones. It's another example of a three-dimensional figure. We take a circle and then the height meets up at some common vertex. Oops, that wasn't very great. All right. So we're going to look at some examples here using geometric modeling. Examples. Example number one, I have typed below, six-sided number cubes are used to play many games. Each edge of a standard number cube is about 20 millimeters. Each of the six faces of the number cube are uniquely cast with dots called pips. The number of pips denotes the number associated with that face of the number cube. What is the surface area of a number cube after the pips have been cast if the diameter of each pip is 5 millimeter? So I'm going to draw what we know a dice looks like, or a die, I should say. I'm going to draw just a square first because they are cubes, right? So each face is a square. Here is my cube. And again, they have these dots, right? Each of the six faces, we have six faces of this number cube, are cast with dots called pips. So you know that this side maybe has two dots on it. One dot on this one, three on this one, right? But there are six faces overall. Also, something I kind of skipped over, which I meant to draw on this diagram, each edge of the standard number cube is about 20 millimeters. So the edge is the side length where the two faces or any two faces meet. So this is 20 millimeters. This is 20 millimeters. This is 20 millimeters. We want to find the surface area of a number cube after the pips have been cast. So after we take the pips away. So I need to find the surface area of the cube, and then I need to find the area of the pips and take the pips away from that surface area. So let's draw out a net of a cube. So if I think about laying all of the faces of a cube flat, there are 6 of them in total. And like I've done before, I oftentimes like to draw a rectangle, kind of divide it up into 4. And there are a couple ways you can do this, but divide it up into 4. And then I draw maybe one face here, and another face on the opposite side here. All right, now again, we should have 1 through 6 on our dice. So 1 here, maybe I'll do 2 here. This has 2 pips in it. This has 1, 2, 3 pips in it. This has 1, 2, 3, 4. We have 1 with 5 and 1 with 6. So altogether, if we count 1 plus 2 plus 3 plus 4 plus 5 plus 6, there are 21 pips in total. And that's super important. And each pip has a diameter of 5 millimeters, right? It says the diameter is 5. So let's note over here, 1 pip is a circle that has a diameter of 5. So if our diameter is 5 millimeters, our radius has to be half of it. The radius is 5 divided by 2, or 2.5, 2.5 millimeters. Let's start finding some areas. So we need the surface area of the cube. And first I want to find the area of one face. So we'll do that here. The area of one face, you're just going to multiply 20 times 20, right? The side length times itself, or 20 squared even, you could think about it as. 20 times 20 is 400 millimeters squared, because side length is 20 millimeters. Therefore, I can put this all together, find the surface area, which we oftentimes like to abbreviate as SA. Surface area would be 6 times this 400 millimeters. 6 times the area of one face. 6 times 400, which would give us 2,400 millimeters squared. So that's the surface area in total without taking the pips away. Now let's find the area of one pip. Do this in orange. The area of a pip, since it's a circle, we're going to use pi r squared, but our radius, like I noted up here, is 2.5. So I'm going to say pi times 2.5 squared. And if you square 2.5, you actually get 6.25. So this is 6.25 pi millimeters squared, which we could get the decimal version of that, but I'm going to wait until the end. Now we have 21 of these. So I have 21 times the area of one pip, means I'm going to multiply 21 times this 6.25 pi. And if I multiply just 21 and 6.25, that produces 131.25 pi, still, millimeters squared as the area of all of the pips together. So this is the area of all pips. Okay, so putting this together, I'm going to find our surface area that we wanted to find, right? After we take away the pips, what is the surface area of a number cube after the pips have been cast? So I'm going to take those away. So I'm going to write out up here, surface area is that 2,400, the surface area of the cube, minus the area of all of the pips, minus 131.25 pi. Again, this is the area of all pips. And when you subtract that, you can use a calculator to do so. You can use like one of these handheld ones, or Desmos can do the pi button for you, or you can use 3.14 for pi and kind of approximate it that way as well. But when you do this, the difference you get is 1,987.66596. And the problem, I believe, did it ask to round? It did not. So let's just round to the nearest hundredth. So I'm going to say this is approximately 1,987.67, since the 5 after the 6 would cause us to round up. And surface area is a square unit, so this would be millimeters squared. All right, one more I want to do. Number 2. Let me move this. There we go. Chocolate-covered blueberries roughly resemble spheres in form. If you measure the outer diameter of one chocolate-covered blueberry to be 3 centimeters and the thickness of the chocolate measures 0.5 centimeters, how much chocolate is used in one of the chocolate blueberries? And by how much, that's talking about volume, how much chocolate, we would measure that in volume of chocolate. So let's draw a picture of this. They're spherical in form, so 3-dimensional circles. Oops, that's like an ellipse. So here's the chocolate that is encasing this blueberry. Now the chocolate is 0.5 centimeters thick. So maybe it looks something like this. Oops. Now, the diameter of the entire chocolate-covered blueberry, right? The outer diameter from one end all the way across to the other through the center, that is 3 centimeters. And it says that the thickness of the chocolate, so from the outside to the blueberry, right? The thickness of the chocolate is 0.5. So this is 0.5 centimeters. This is also on the opposite side, 0.5 centimeters. So in general, we're going to need to find the volume of the sphere in total, and then subtract away the volume of the blueberry. And then what we have left should be the volume of just the chocolate. So the volume of a sphere is 4/3 pi r cubed. So we're going to actually need the radius, and the radius of the outer chocolate, right? Blueberry, chocolate, and all. We know the diameter is 3, so this means then that the radius is 3 divided by 2, or 1.5 centimeters. So I am going to do this next step in orange. I'm going to say the volume in total is equal to 4/3 pi times our radius, which is 1.5 cubed. And 1.5 cubed times 4/3, interestingly enough, is actually 4.5 pi. Then if I multiply 1.5 to the 3rd power, and then I multiply that times 4/3, that gives me 4.5. And then we still have the pi in the mix. All right, and this would be centimeters cubed as our volume. Now we need to find the volume of our blueberry. So let's see, volume of the blueberry. I guess I could have just done berry, but that's fine. We know the entire thing is 3 centimeters, and it is 1/2 centimeter thick on both sides. So if I subtract away 1/2 centimeter on one side, 1/2 centimeter on the other, that's a whole centimeter in total. That leaves us with 2 centimeters as the diameter of our blueberry. So this is 2 centimeters here, which means the radius is half of that. 2 divided by 2, or 1 centimeter. So the volume of our blueberry is a little bit more straightforward. It's 4/3 pi times our radius, which is just our diameter 2 divided in half, so 1 cubed. So this is just 4/3 pi times 1, and 4/3, that is 1 1/3, or 1.333, repeating forever. I'm just going to leave it at 1.33 pi centimeters cubed. So if I want to find the volume of just the chocolate, the volume of the chocolate is the difference between the total volume and the volume of the blueberry. The total volume, which was 4.5 pi, minus the volume of the blueberry, which was 1.33 pi. So what do you get when you subtract 4.5 pi minus 1.33 pi? And now is probably the time to switch over to a calculator if you would like. And when you approximate this, were we asked around? This one, I absolutely did have it originally, and then it got cut off. We're going to round to the nearest hundredth. So when you put this in your calculator originally, you will get 9.9483 going on. So rounding to the nearest hundredth, that's approximately 9.95. And again, the unit here would be centimeters cubed, because we're measuring how much chocolate, and that would be measured in volume. Please let me know what questions you have on this, and I look forward to seeing you soon.